Welcome back to Ocean 201. We're going to continue our discussion of deep sea sediments with focus on biogenous sediments and how we sample deep sea sediments. So biogenous sediments, the two that mainly show up in our deep sea, at least that show up and are preserved for a long time, are calcareous sediments and siliceous sediments. Now, calcareous sediments are formed from organisms that have shells made out of calcium carbonate. The two primary types of these are coccolithophores. They make these little plates, and foraminifera, which sort of look like little popcorn kernels. These are both very important, especially to our long-term dating of sediments, because they retain a signature of surface isotopes. And we'll talk about that a bit later. Now, siliceous organisms, these are primarily diatoms and radiolaria, and they form essentially glass silica dioxide shells. These are both calcareous and siliceous organisms. Really, their shells are quite beautiful, I think, and really kind of remarkable that these are preserved and that you can see them you can look back in history and find these throughout these sediment cores. Now, areas where we have large concentrations of either calcareous or siliceous shells are called biogenic oozes. The oozes is the technical term, and these are any pelagic sediment that contains greater than 30% of skeletal material. And we'll talk about where those form as well. One important thing to note about these shelled organisms is that the weight of the shells help them to sink faster. So later on in the semester, we'll talk some about carbon export and how biology impacts the transfer of carbon from the surface ocean down to the deep ocean. And that can be mediated or accelerated if you have a larger portion of organisms that have these hard shells that weight them down when they die and help them to sink out. And pelagic, as we discussed, means open ocean. So just, it's a good word to remember and one you should know. Now, these shells don't accumulate uniformly on the sea floor. Depending on where they settle out, they might dissolve or not. So the carbonate compensation depth is essentially a horizon in the ocean below which calcium carbonate shells tend to dissolve and above which they can accumulate. And the reason there is this depth is because the solubility of calcium carbonate varies in the ocean. So at deeper depths that are colder and have lower pH, you can dissolve more calcium carbonate. This depth horizon is relatively fixed in the current ocean. It's at about 4,500 meters, although it shoals in the Arctic and Antarctic at the poles because you have colder, more acidic water coming up closer to the surface. This can vary over long time periods. And this is another of these feedback mechanisms that can control the global climate. By adjusting where this depth is in the ocean, you adjust how much carbon the ocean can hold, more or less, and that then in turn impacts the carbon that goes in the atmosphere and is part of this larger climate cycle. And we'll talk more about that later in the semester. And so but the main thing to know for now is that this lysocline, this depth-dependent horizon, or this latitude-dependent horizon that identifies a uniform chemical property, that's what a lysocline is, that determines where you have the accumulation of calcium carbonate and siliceous materials. So below, in areas of the ocean that are deeper than the lysocline, calcium carbonate dissolves and siliceous materials can accumulate. In areas above the lysocline, you can have calcium carbonate accumulation. You can still have siliceous material accumulation, but the calcium carbonate tends to overwhelm those areas. Now, another type of sediment are hydrogenous sediments. These are, as we discussed, not one of the dominant types of sediments, but they can be quite important. And these are minerals that precipitate directly from seawater. So we also call them autogenic, meaning they form in place. And so one of the main types of these are iron manganese nodules. These are layers of manganese and iron hydroxides that form around a core. They also have other heavy metals and precious metals. These form extremely slowly. So this cross-section here, for this we're looking at a cross-section of one of these nodules, and this cross-section is about 7 centimeters across. But the accumulation of this material is about 1 to 10 millimeters per million years. So they accumulate extremely slowly. They are a potentially valuable resource for extraction companies. They're a way to get these rare metals in relatively high concentrations. And so there's a lot of exploitation that is being explored through deep sea mining. And that's actually something that a number of people in the oceanography department here study, is the impact, the formation and the impact of these nodules and what impact mining would have. And so disturbances here, because of the slow rate of formation, any disturbance can last for a very long time. So for example, there were some experiments done in the 70s where they harvested some of these nodules, and the tracks, the impacts of those experiments, you can still see 50 years later. Other types of autogenic sediments, they've got non-biogenic carbonates, so oolite sands. These are calcium carbonate granules that precipitate abiotically from seawater, so they're not part of shells. Evaporites, salt deposits that form as water evaporates when you isolate parts of the ocean or in landlocked seas or lakes, and hydrothermal vents. All right, so sediment thickness. Where do we have lots of sediments? So this color scale here demonstrates the thickness. These light or the dark blues are the shallowest sediments over the ocean floor. As you get into the greens and the reds, you get sediment thicknesses that are approaching 10,000 meters or so. We see a few different things here. So for example, in the Atlantic, in the middle of the Atlantic, we have very thin sediments, as we do in the Pacific. These are both spreading regions, so the seafloor is very young, hasn't accumulated anything yet. But overall in the Atlantic, the average thickness is about 1 kilometer. So that's averaging both these thin areas and these very thick areas, where in the Pacific, it's much less. And a large part of that is that the Atlantic has very thick sediments around the coasts, in part because you have river deposition. So you've got the Amazon, the Mississippi, and the Congo all flowing into this basin. And it's both a smaller basin than the Pacific, and it has a lot more sediment load. So the combination means that you can get a much greater sediment accumulation along the coast. And the second reason is that the Atlantic primarily has these passive margins where sediments can accumulate. You don't have the active margins with subduction and destruction of the ocean plate. So that those are the two reasons why we have much thicker sediments in the Atlantic than in the Pacific. All right. So deep sea sediment distribution. So we talked about the terrigenous and biogenous sediments, and this schematic shows where we can find them. So we get continental margin sediments, this light taupe color along the margins of continents, glacial marine sediments in places like Antarctica, where you've got lots of glaciers flowing off into the ocean and depositing sediments. Pelagic clays, so these are out in the middle of the ocean where you have really fine particles that eventually settle out into this really fine mud on the bottom of the ocean. And then biogenous deposits. So we have calcareous deposits, primarily closer to the tropics, although extending out into the subtropics significantly. And then in the higher latitudes, where, as I said, that calcium carbonate condensation depth goes closer to the surface, is shallower, that's where you have dominant siliceous oozes. So we get large diatom blooms in the North Pacific and all along in the Southern Ocean. And there, in those sediments, you have primarily siliceous material, not calcium carbonate. We also get some radiolarian oozes in the equatorial Pacific as well. And then these H symbols represent places where you have hydrogenous deposits, so manganese nodules. And so one that's important for the Pacific is this H here. This is a Clarion-Clipperton zone. And this is both a site of ongoing research here at the University of Hawaii, as well as a site that is likely will be exploited for minerals in the near future. So that's one of the reasons to study it, is to understand what impact that resource exploitation will have. Okay, so how do we actually learn about the sediments? How do we sample these sediments? So there's a number of different ways to get cores of sediments. If you're just going for the very surface of the sediment, you can use something called a grab sampler or clamshell sampler. These don't go very deep, but the idea is that they scoop into the sediment, leaving the structure somewhat preserved so you can pick it up and put it down. Now, you don't always get a nice clean sediment core from that. And so instead you can use gravity cores or piston cores. And these are different ways of drilling down into the sediment and retrieving a representative sample that maintains the layers that people are interested in. So if you want to go down deep into the ocean, these clamshell samplers or box cores don't work. Then you have to go into piston cores or drill ships. And so these piston cores can essentially, there are these large cylinders that are lower down. Once they get close to the ocean floor, you release a weight. So this weight, when it hits the ocean floor, it then relieves the tension, and that really lets the core fall down and plunge into the sediment with the weight of the core. Then once that piston, or once that core touches the sediment interface, a piston is driven deeper down into the surface. And so that can go down about 25 meters. And it is very good at preserving the structure of sediments in a way that these samplers cannot do. And so 25 meters is a lot that can cover a lot of time in terms of the record down in the sediments. But for longer cores, you need to go out on drill ships. So this is an example of an ocean drilling ship. It looks, basically is what it looks like. It's got a large drill platform on top of a ship. And so these can drill down into the ocean sediment they can go very deep, many thousands of meters. There's an international deep sea sampling program that goes out on ships like this to drill in different locations around the ocean. This is the deep sea drilling program. Used to be the ocean drilling program. It's now the International Ocean Drilling Program. And this is one of the ways that people were able to confirm the plate tectonic theory. Now, there are large repositories of these cores. This is a picture, I believe, from Lamont Doherty, but University of Hawaii Manoa has some cores stored here. And the reason that you store the cores is then you can go back, and as you have new ways of sampling the material, people can go back and make new measurements. So that wraps up our discussion of deep sea sediments. So we talked about how sediments are these loose and unconsolidated particles that can be both organic or inorganic, and they accumulate on the ocean floor and provide essentially a memory of the ocean, and can tell us a lot about the past climate, past sea level, a lot of important things that we can learn from them. We talked a bit about size classification and how that impacts where sediments end up. We focused mainly on the sources classification. So when you're thinking about studying, I'd focus on the sources and think about Hydrogenous, Biogenous, and Hydrogenous sediments. We didn't talk much about cosmogenous sediments, but it's good to know that you do get some sediments that come from space. Location is another way to classify sediments, either neritic, or nearshore, or pelagic, but primarily focused on where you get different oozes, so calcareous oozes, siliceous oozes, or abyssal clays. We talked about the calcium carbonate condensation depth. That's an important concept to learn and one we'll revisit later. And then we talked a bit about sediment depths and sampling distributions and how we actually measure them. And so with that, we will wrap up.